Thanks, Margaret. Thanks, everyone. So I'm Steve Finkelstein from UT Austin, and I'm going to talk to you about the CEERS survey, which is the Cosmic Evolution Early Release Science Survey. And on this title slide, I'm just showing the COIs on our team. So we had about 18 COIs from a number of places around the country and around the world. The full CEERS team is about 100 people, so about 18 COIs, about another 80 collaborators or so. At the bottom, I'm putting our Twitter handle. If you go there now, there's not a ton. In fact, the only tweet in the last 2 years was one I sent yesterday advertising this webinar. But we have a website under construction, which is almost ready. And once it is ready, we will post it there. So if you want to find out that information, you can follow us on Twitter, and that account will get more active as we get closer to launch. So this figure is, like most of the figures come straight from our proposal, this is sort of our strategy map. And so our main science driver, as I'll get to, the primary science driver is to find galaxies at the earliest redshifts, at the earliest cosmic times. We also wanted to be able to demonstrate efficient JWST parallel exploration of a high redshift universe. And so we really wanted to do as much imaging and spectroscopy as we can, ideally focused on one part of the sky where we can get overlap of the instrument. And so we're going to be observing with a number of different modes, including NIR Cam imaging, both at short and long wavelengths, NIR spectroscopy, both at R of 100 and R of 1000 resolution, NIR Cam Grism slitless spectroscopy, which is at R of 1500, and then also MIRI imaging over a wide range of filters. And as I'll show you in a minute, a lot of these overlap. And so some of the validation tests that we're doing for future surveys with the telescope are validating coordinated parallels. And so we're doing both NIR spec with NIR Cam and MIRI with NIR Cam. We're going to do an analysis checking the slit loss calculation for NIR spec MSA observations. We're going to explore the R of 100 versus R of 1000 Grism for the same sources so that people can take a look and figure out what might be best for their future surveys. And then finally, we'll explore different MIRI filter pairings. So we're using a number of filters, but for your survey, you may want to use fewer, and you can use ours. And so in addition to finding the earliest galaxies, which is going to be primarily with the NIR Cam imaging, our spectroscopic survey is going to provide a large spectroscopic sample of galaxies at very high redshifts. We will have the first large sample of spectroscopically confirmed galaxies in the epoch of reionization through rest frame optical emission lines, which we think from Spitzer IRAC colors are very, very strong, so we should see them. But we are also going deep enough to see weaker rest frame ultraviolet emission lines, which will allow us to do nebular modeling of the star formation regions in these galaxies. At lower redshifts, we'll be able to do even more detailed chemical evolution studies of galaxies with the spectroscopy, study the ionization in these environments, maybe even the pressure in the interstellar medium. We'll be able to study supermassive black hole growth from redshift 1 all the way out to redshift 7, searching for some of the earliest black hole seeds in the centers of galaxies. And at the lowest redshifts that we'll explore, redshift sort of 1 to 2, we'll use the long wavelength MIRI imaging to characterize mid-infrared diagnostics of star formation, dust attenuation, and AGN evolution. And so the idea behind CEERS is that if you study galaxies and you don't care about which specific galaxy you're studying, so say you're studying redshift greater than 0.1, this survey will have something in it for you. And so this figure here shows our observing plan. So our primary field, and the one we're really hoping to stick with, is the extended Groth strip. This is one of the 5 candles fields. And the reason why we want this field is it has one of the largest observability windows in the field, and it works out that you can observe it at a position angle that allows us to get maximum overlap between the filters. So this particular layout shows observations during the month of December, which is where we will observe given the nominal launch date of March next year. If launch slips a little bit, we can also do this in June. The whole thing would split by 180. And so we have 10 different pointings with NIR Cam, and you can see they're each labeled number 1 through 10. And you'll see 2 little blue squares for the 2 NIR Cam modules labeled number 1. Those 2 blue squares go with the green square labeled number 1. That's the MIRI pointing done in parallel. And so NIR Cam pointings 1, 2, 3, and 4 go with MIRI pointings 1, 2, 3, and 4. And then NIR Cam pointings 5 through 10 go with the big red squares, which show where NIR spec will fall for NIR spec pointing. On NIR Cam, we are doing 3 different filter pairs. So F115, W on the short wavelength side with F356 on the long, 150 with, 115 with 277, which actually isn't listed in that table, so it confused me, 150 with 356, and 200 with 444, And then in a few of the fields, we'll have an extra exposure. We'll actually get a little bit of 410M. The nominal point source depth, 5 sigma point source depth, is about 29th magnitude. We are going double the exposure time in the bluest band, F115W, because that acts as the dropout band for a high redshift galaxy. With NIR spec, we are doing the 3 middle resolution gratings. We should get emission line fluxes down to a couple times 10 to the minus 18. So this is on par with the deepest ground-based surveys that have been done, but of course without those pesky night sky emission lines. And in the PRISM observations, we should actually significantly detect the continuum from sources down to NIR Cam slitless spectroscopy, that's in those cyan hatched regions you can see in the middle from pointings 3 through 6. We should get down to emission line fluxes at about 5 sigma, again, about 8 times 10 to the minus 18. And with NIR Cam, you also need to pick a filter, and we are using the F356W broadband filter. And we did a trait study trying to weigh sort of excitement of the science, how high redshift we could go versus the rising background as you go to longer. So F356W was a clear winner there. The idea there, the primary science case is we can look for oxygen 3, the rest of them also called oxygen 3 emission line from galaxies at redshift 5 to 7 without pre-selection. And finally, we have 4 MIRI pointings. MIRI pointings 1 and 3, these are the ones that overlap with all of our data sets. And those 2 pointings, we're going fairly deep in just the 2 bluest bands, F560 and F770. And the science goal there is high redshift, to study rest-frame optical and even rest-frame near-infrared stellar emission from high redshift galaxies and get very robust stellar masses. In MIRI pointings 2 and 4, we're going more shallow, but we're splitting it across 6 filters from 770 all the way to 2100. And that's for the redshift 1 to 2 dust emissions. So as I mentioned at the top, our primary science goal was to study the very earliest generation of galaxies. So the most distant galaxy that Hubble has found is at about redshift of 11. There's only one that we found at that redshift and only maybe a couple at redshift greater than 10. And so we explored a number of different model predictions and actually a wide range of potential survey strategies and found that in sort of a fixed program time of 50 to 60 hours, we can maximize the number of high redshift galaxies we get with sort of a wide and moderate depth survey, which is why we've done this style of survey. And we, of course, don't know what that universe looks like because we've only seen a few galaxies, but we can take a cue from models. And what this figure is showing is the cumulative number density of galaxies brighter than the CEERS survey limit as a function of redshift. And the different colored lines or shaded regions show different models, and the gray points show observations from Hubble, primarily from candles. And you can see at the low redshift and redshift 7, models agree with observations pretty well because the observations agree with each other and the error bars are small. But as you go to higher redshift, these models fan out. And so at redshift 10, if we take the most optimistic model, we should find maybe 30 to 40 galaxies and maybe 10 to 15 at redshift greater than 11. If it's one of the more pessimistic models, maybe we'll only find a half dozen at redshift 10 and maybe 1 or even 0 at redshift 11 to 12. And so the thing that is changing in these models, there are a wide range of things that are changing, but the biggest one is the star formation efficiency. And so if the star formation efficiency is inefficient, much like it is in today's universe, you would expect something like the red model. But if it is more efficient, if the star formation loss scales with the gas density, which some other models predict, as the universe gets more compact at early times, the gas density in the interstellar medium in galaxies is more dense, and the star formation efficiency may go up. That's something like the green or blue model, and we may see more galaxies. And so beyond just the excitement of finding these extremely early galaxies and understanding their nature, their chemical enrichment, their stellar masses, we can actually begin to constrain the small-scale physics of star formation in the interstellar medium. Science goal number 2 is based around spectroscopy. So this figure here, the top figure shows 2 different simulated spectra. And so these are redshift 6 galaxies at the brightness of which we will observe in CEERS and with noise comparable to the CEERS exposure time. And we're showing 2 models where the ionization parameter differs by an order of magnitude. And so if you look at the inset, we're exploring the oxygen 2 and neon 3 lines, which are close together. And it turns out that ratio can constrain the ionization parameter very well. Number 1, because they're close together in wavelength, so they're reddening independent. And number 2, you can see how in the low ionization parameter model, oxygen 2 is very strong and neon 3 is weak. And in the high ionization parameter model, oxygen 2 almost completely goes away. All the oxygens ionize into O3, and neon 3 becomes quite strong. And so what we're actually showing in the lower panel is a line diagnostic ratio diagram of O3 to H beta versus neon 3 to O2, and we will observe these for several dozen, if not close to 100 galaxies at redshift 6, and we can actually begin to constrain simultaneously the metallicities in these galaxies, the ionization parameters in these galaxies, and what fraction of the ionization may be coming from AGN. And so the table on the right shows the number of objects in slits. This actually comes from our original proposal. And so we have about 330 slits across our 6 pointings in the R of 1,000 mode, about 30 to 35 at redshift greater than 6, about 100 between redshift 3 to 6, and the rest at lower redshift. And we have sort of a comparable number in the prism mode. These will actually improve. So we've been talking with the NIRSpec instrument team, and they have their own multi-slit planning software that places objects more efficiently, particularly in the prism mode. And so we think that the R of 1,000 numbers will go up by maybe 15 to 20%, and the prism numbers will roughly double. And they're also talking to Space Telescope about trying to get these improvements into the APT version of the MSA proposal. And finally, the third science goal, there are more than 3, but I'm only going to talk about 3 today, is twofold. The first one is that CEERS is going to unveil high-resolution rest frame optical morphologies for fairly high redshift galaxies at redshift 2 to 3. This particular image here is showing a real image of a redshift 2 galaxy in Spitzer-Iraq imaging at 3.6 micron on the left. And on the right, we show a NIR Cam simulation. This is of a galaxy from the Illustris model, showing the, of course, substantially improved spatial resolution from Spitzer at these wavelengths. You can actually begin to explore the morphologies of these galaxies, study stellar populations across the face of a galaxy. This figure now at the bottom left shows a simulation of our longer wavelength mirror imaging. So on the left, we show a region of the candles field in the H band. In the middle, we show the real MIPS 24 micron image of this field. And you can see something is emitting hot dust, light from hot dust. You don't know which one. But at the MIRI resolution in the right-hand panel, this is a 3-color image made from 10, 15, and 18 micron filters. You can actually basically resolve every single source. And you can see, of course, we made some assumptions about how we split the light between these galaxies, but you would be able to tell which objects are emitting, which aren't, and what the dust temperature is. And so one of the things you can do with this is to study the main sequence of star formation in galaxies, so star formation versus stellar mass, to an order of magnitude deeper in star formation than was possible with the previous generation of Spitzer MIPS studies. And the main advantage here is you are observing the dust emission directly, not trying to extinction correct the rest in UV, which we know does not work very well once galaxies get modestly dust. So with some more examples of what CEERS will be able to do, this is an example observation of a real galaxy we think that's at redshift 9. So the top row shows real images of this galaxy in Hubble with C3 and in Spitzer-Iraq. And so we detect it in 2 WIF-C3 filters and just barely detect it in the 2 bluest Spitzer-Iraq bands. That is in a couple hours of exposure time with WIF-C3 and in 50 hours of exposure time with Spitzer. This is an object in the EGS field that CEERS will observe. And on the bottom, we're showing a simulation of what this galaxy will look like from 1 all the way out to 8 microns in just 3,000 seconds of integration. So we will detect it at 15 to 20 sigma significance in all the NIR Cam bands, and even detect it at 5 to 8 sigma in the JWST mirror. So we'll be able to model the stellar population, measure the stellar mass very robustly, measure the dust attenuation in this galaxy, and begin to constrain galaxy formation at the earliest times. This is a highlight of how if you didn't have the MIRI imaging, you could still model the stellar population fairly well, but the stellar mass would be a bit uncertain. And so MIRI can help constrain the stellar mass of these galaxies. Those are those 2 MIRI pointings 1 and 3 from the original figure. And on the bottom, I'm showing another NIRSpec simulation. This is now of this same redshift 9 galaxy. And not only will we detect these very strong rest frame optical lines, we'll detect some weak rest frame optical lines, and we also think some weak rest frame ultraviolet lines. Again, only in about 3,000 seconds. This is I actually already showed this. I'm going to skip this one. OK. And so I mentioned we're doing a NIR Cam Grism component. There's a big science case here, of course, but we also want to do a direct measure of slit losses. And so with the NIR Cam Grism, obviously you have to deal with contamination from sources, from adjacent sources. So we're observing with both the column disperser and the row disperser, so we'll have 2 different positioning. But you're going to get all of the emission for a given source. Whereas when you observe with NIRSpec, you have a relatively small slit. And so the NIRSpec reduction pipeline will try to estimate the slit losses, but we want to do an empirical test of it. And so our empirical test is that for some subset of sources, we will have both near-spec observations and NIR Cam Grism observations. The Grism will tell us the real true total emission line flux. And with near-spec, we will have the estimated split loss correction from the pipeline, and we can explore how robust that is and how that depends on where the object is centered in the slit. As the object moves away from center, split losses will go up, and I'm sure that is modeled in the pipeline, but we'll actually test how accurate that is. And the other thing we will do is that for one of our near-spec pointings, we will actually do a repeat observation where we shift the pointing by 1/3 of a slit width in the dispersion direction. So we're taking objects and moving them in the slit and reobserving them again, and we can again explore how robust those split loss corrections. Of course, with the Grism, we want to demonstrate this as a mode for science. This is much more complicated in a variety of ways than the Hubble Grisms, and so putting data out there as fast as possible will help people figure out if this data is really for their science case. And we want to perform a blind search for emission lines at high redshift. That's what I'm most excited about. We think we should find something like 50 very faint galaxies with strong oxygen-3 emission lines. These will all be galaxies we don't know of right now. We will hopefully see them in our NIR Cam imaging, but they're not sensitive. They're not bright enough to be seen in the camera. And this is a simulation that NOR Perscal Space Telescope ran for us, showing how the oxygen-3 and H-beta emission lines would look for different O3 5000 strength. So this is a complicated plot of our deliverables, but I'll just give you the highlights. So the top sort of shows you an updated calendar now. So if the telescope launches in March of 2021, we think we will observe in December of 2021. And then we will have actually 4 releases, a pre-launch one, which consists of re-reduced Hubble mosaics using improved background subtraction and astrometry. And so we hope to get those done this summer. And then we'll have data releases of the CEERS data 3, 6, and 12 months after launch. And basically every data release, we will re-reduce the data using whatever the latest pipeline improvements that are coming out of the Institute, and we'll progressively add the data products. So the level 1 release, which is 3 months after launch, will be just reduced data, no catalog. Level 2 will be a re-reduction of the data. And then on the imaging side, we'll have PSF match photometry catalog separate for NIR Cam and MIRI. And on the spectroscopy side, we'll have a spectroscopic catalog, including line fluxes and spectroscopic redshift. And we also hope by that time to have release a sample of redshift greater than 9 candidates in time for cycle 2 observation. And our final data release about 12 months after we get the data will include, again, a re-reduction of everything, advanced image mosaics, multi-wavelength catalogs, now including NIR Cam and MIRI together, and including some value-added data products like photometric redshift, stellar masses, and star formation rates. We hope to do a morphology catalog. And on the spectroscopy side, we will, of course, update our reductions, our catalog, and we'll also publish our near-spec split loss analysis. The other thing that we want to do pre-launch is, for both ourselves and for the community, is to simulate data from all of our observing modes. And so we are working on that right now for all of our 4 modes, and we will release these to the community once they're ready. And that release will include raw data, so every individual raw data frame, so that you can run it through the pipeline and explore the pipeline. Reduced data, so that you can actually practice your analysis techniques. And also Jupyter Notebook showing how we ran the data reduction pipeline, as well as any pipeline modifications, which we have to do many now, and we're working with the instruments to build those modifications. And this is just a simulation highlighting what we have done with NIR Cam. So this is work led by Michaela Bagley, who's a postdoc here at the University of Texas. And this is a part of our NIR Cam F277W mosaic. These have been generated from a semi-analytic model run by Rachel Somerville and Aaron Young at the CCA in Rutgers. And so we populate the image with this model. We then create raw data frames, read up the ramp, then we pass it through the pipeline, all 3 parts of the pipeline through to the image mode. And so these are the kinds of data products that we will be releasing in the near future. And all of this will be announced on our website. So again, check our Twitter handle, and you'll be able to see when our website is ready to go, and then when we post these things. And so with that, I'll just put up the summary. So CEERS, again, is designed to help anyone who is interested in studying galaxies at pretty much any redshift outside the local universe. So again, if you don't care about the name of your galaxy, CEERS can have something for you. And it's going to include data representative of medium-depth JWST surveys. So again, imaging with NIR Cam from 1 to 5 microns, 5 to 20 micron imaging with MIRI, 1 to 5 micron spectroscopy at both R of 100 and R of 1000 with NIR spec, and 3 to 4 micron Grism spectroscopy with NIR Cam. And as I hopefully convinced you, we're dedicated to rapidly releasing high-quality reduced data products and catalogs. Yeah, we hope to communicate with you both through our website, through webinars such as these, and through Twitter, which are all in the process. And so with that, I will take any questions.
Thank you, Stephen, for that very informative talk about high-Z galaxy surveys. Do we have any questions from people online? If you do, please unmute yourself. All right. Well, let's see. I have a question. So this is pretty formidable. You're going to be surveying this pretty extensive field and producing catalogs. And what do you anticipate in terms of the community doing stuff with this? Do you think they'll do? Do you think the archival work will be enough, or do you think people are going to grab these things and say, "Oh, I need to do follow-up spectroscopy with it"? What do you anticipate?
So both. Certainly, the amount of science that you will be able to do with this data set is there's a lot of data and a lot of different observing modes coming in, and so I anticipate lots of archival proposals from our team, but from across the community. I focused on a few of the key science cases, but just to throw you a random one out there that we realized actually got cut from our proposal for space is Paschen alpha emission. So we'll detect spectroscopically Paschen alpha emission from large numbers of galaxies at redshift 1 to 2. This is the gold standard star formation rate. That's something that you might not think of when I'm up here talking about redshift 10 galaxies, but that's an example of something. In terms of follow-up, also correct. So certainly we're going to be discovering new sources that will be very interesting to obtain spectroscopy of. We'll also find some features in our relatively shallow spectroscopy or low resolution spectroscopy that people will want to follow up deeper or at higher resolution. And we're not using all of the filters on all of the cameras as well. And with MIRI in particular, we're not covering a very large fraction of the field. And so I do predict that people will put in a number of observing proposals to add data to this field. I'll say one of the advantages this field has over, so there are 5 candles fields, 2 of them are pretty heavily dominated by the GTO team, so they're really not available for GEOs to propose for. And out of the other 3, EGS, Cosmos, and UDS, although EGS is not observable from the southern hemisphere, unfortunately, it does have the lowest background. And so if you want to observe in Cosmos, for example, you're going to take a magnitude hit of a couple tenths of a magnitude, and it could get worse the longer you go. So this field, I predict, will be pretty heavily observed.